Okay. So, hello everyone. Welcome to the week 8 of problem solving session for the theory of sorry. Yeah. For the NPTEL course on theory of computation, and yeah. So last time we briefly saw this concept of undecidability, and we also saw what are reductions. I mean, okay. So when do you say that a language L is not decidable? If that does not exist, um, yeah, total Turing machine computing or accepting L. Okay. So one such example of undecidable languages, maybe the first example that we saw was halting problem, which is the set of all m comma x such that m does not halt on x. And similarly, we also can define um, a similar problem which is called membership problem. So it is very similar. Given m comma x, m does not accept x. Okay, so these are uh, some problems that we for which we know that there cannot exist a total Turing machine for these languages. So if we recall the Venn diagram that we have the set of semi-decidable languages here, we have co-semi-decidable languages here, and their intersection is exactly what is the set of decidable languages. And halting problem, membership problem, all of them, they sit here, and if you look at their complements, then they'll be in the complementary set. Even uh, what is ATM?
So that was the acceptance of a string. I mean, ATM was m comma w, wherein w is accepted by the Turing machine. So what's the difference in between the ATM and the halting problem then? Is this the difference of halt, or I mean, what the
So
difference is?
ATM would be, if it's defined that way, then ATM would be the complement of MP, because then this the complement of this set would be the set of all m comma x such that m accepts. Oh, okay. The complement is not. Oh, right. Yeah, such that m accepts x. So that is exactly what ATM is.
So m accepts x and then m halt on x. Uh,
Hmm.
so what's the difference? I mean, in halting problem
Oh,
and ATM.
oh, okay. So you're asking the difference between this and this.
Yes, yes.
Huh.
So
So,
what is the statement of the halting problem? M halts on X or M does not halt on X?
oh, okay, okay, okay. You're right. So, yeah, you're right. So this is, yeah, what I defined was the complement of, yeah, m holds on x and m accepts x. Yeah.
So if M accepts X, then usually we call this problem as ATM, because while proving that halting
Hmm.
is undecidable, we reduce ATM into the halt.
Hmm. Yeah. Then both are the same.
Yes. Yes. So are they same? I mean, instead of MP, probably the name is ATM, I guess.
Hmm. Yeah. That's
Or
it. Yeah.
yes. So what's the difference? I mean, in between these two
Between
problems?
HP and ATM.
Yes.
Huh.
Yes.
So, um, I mean, see, there can be machines um, that are in this set but not in this set, because it is possible that m rejects x, therefore it halts on x. So that m, so there could be, for a fixed m, there could be an x such that this is in HP because m rejects x, but that particular input will not be in ATM. Similarly, there can be instances which are here. No, okay. Everything that's here should by definition be here. That is true, but they are not same as sets.
Right. So how do we define the rejecting states in the Turing machine then? While representing a Turing machine, we still use double circle to represent the halting state. So how do we represent that? Okay, these states are the accepting states, and these states are for the rejection,
Hmm.
and then remaining states could be anything.
Huh. So in the seven tuple definition that we had q sigma. Uh, yeah, I think you put your blank symbol also here.
Yes, Q sigma delta, Q naught
Uh,
F tau and blank.
mm, F, no, F is not. Yeah, wait, sorry. So QA is your accept state, and Q or QT, it's denoted by QT generally, or just let's say T and R. So this is the accept state, which is a special state, and this is a reject state. Um, yeah, which is a special state, which is given in the description of the machine.
Okay,
What
and
else
then
do
while
we have?
drawing the Turing machine, how do we represent rejecting states there?
Uh, no, it's just that that state is labeled R. So you know that if you reach the state R, then you're going to reject. I mean, the circle thing and all, it's just a matter of notation. So, um,
Yeah, yeah, right.
hmm,
I understood. So the difference in between this SP and the ATM is, I mean, lies only in this rejection thing.
hmm,
That there is a possibility of getting rejected also.
hmm,
This haltness, and whereas in the second problem, it has to be accepted only, and no other option.
hmm. Yes. So
Yeah, all
M
right.
is delta here. Yeah. Okay. Good. So,
Ma'am, in what context has the term halt been used here?
um, so, um, so I mean, if you have a Turing machine, okay, it's not necessary that it will either accept. So accept or reject, it could just keep on. For example, you can imagine a Turing machine whose description is as following. It just uh, so here is some input written on the top of it, and what it does is it just keeps moving to the right. So the only thing it does is it no matter what you read, it keeps moving to the right. That's all. Okay, and since the tape is infinite on the right, what will happen is it will um, never accept or reject. It will just keep moving, or in other words, it loops. Um, so so it's not going to stop and say that okay, accept this string or reject this string. It will just keep running forever. So we such machines, we say that they do not halt on that particular input. So if this machine just m is as follows, it no matter what state you are in, no matter what you read, you're just going to um, keep moving to the right. Okay, so this m um, runs forever, or in other words, m does not halt. So that's what we mean by it does not halt. It doesn't accept or reject, it just keeps moving.
And blank is used which purpose?
since the tape is infinite, um, blank is just, I mean, so initially, so this part of your tape is the input that's given to you, which is finite input. Beyond that, I mean, it just, I mean, there are just blanks written and you can overwrite it. That's all.
Ma'am, keep moving is a term you have been used. So means what is keep moving here?
Meaning, so every time you read, so how is the transition function defined? You have q cross uh, gamma to q cross what are you going to write, and whether you're going to move to the left or right or stay, right? So let's say you are here, this is where your head points right now, and you are at some state q. Then what does the transition function tell you? You look at the state that you are in, look at the current symbol on the tape where the head is pointing. Based on that, you decide which state to go to. This q part is similar to what you used to do for DFAs also, right? You read something and you decide what state to go to, and this comma allows you to write something on the tape. So if you don't want 0 to be here, you want to change it to something, this comma tells you, okay, you look at the function and write something else here. And then left or right tells you whether you are going to go to the left or go to the right. So when I say keep going, I mean that uh, it just keeps, so because of the way we have defined this transition function, what it does is it just keeps moving right. No matter what it says, it just keeps moving right. So it will always, I mean, keep on running forever because the tape is infinite to this end.
Ma'am, it is for only for 0 1 or means binary, or it is possible for decimal or octal number.
So generally we represent finite inputs. So I mean, the representation is not an issue, you can always convert it to binary. But like, since you deal with finite inputs, those are generally integers, or you cut it off to some point. But technically you can represent an infinite number as well, because because the tape itself is infinite. Yeah.
Okay, ma'am. You continue with your agenda.
Cool. So okay, so this is just a recap of yeah, the definitions of the semi-decidable and co-semi-decidable sets, and the languages that we saw in there. And one way to show that a language is undecidable is that one way is the diagonalization argument, and second way is that you do reductions. So what is the idea? If you say that A reduces to B, um, if there is a computable function um, f from sigma star to sigma star, such that x in A, if and only if f of x is in B. That means if some string is in the set A, then the corresponding mapping of x, which is f of x, should be in B. And if some string is not in A, then the corresponding f of x should not be in B. And this function can be a many one function, because there can be a lot of strings here that get mapped to one one string only. That is totally fine. If f is many one, then we say that the reduction is many one. Okay, that's all. So the idea of doing this is that if I know that if B is decidable, okay, then what can we say about A?
So if B is decidable, then I mean B is at least as hard as the problem A is, and B could be harder than that. And since B itself is decidable, so therefore A would also be decidable.
Yeah, then A is also decidable. So if you want to show that some language is decidable, uh, then what you do is you reduce it to some decidable language so that you can uh, use the solution of B to get a solution of for A. Whereas if you want to show that some language is undecidable, then what you do is you take your undecidable language. So let's say then what I could do, for example, is I'll reduce A to HP, and because sorry, the other way around. Yeah, then I'll reduce, yeah, then I'll reduce HP to A. Okay, and since HP itself is undecidable, that means A must be undecidable. So it's just the contraposition of the previous statement. So um, this would imply that A is undecidable. So if you want to show something is undecidable, you reduce some hard problem to it. If you want to show it is decidable, you reduce that problem to some easy problem. So it's just that direction is opposite depending on what you want to show. Okay.
Is there any constraint over the time? I mean, is it necessary that F should be polytime computable or not
No.
necessary?
So in case of so when we talked about these sets itself, right? We never talked about how much time it takes to accept. Right? It could take exponential amount of time, but that was fine by us. So therefore, we cannot introduce notions of time here because these languages themselves don't have a notion of time, right? So yeah, all that matters to us is that it should be a computable function. It should be a semi-decidable. Sorry, there should be some Turing machine that computes it. Total Turing machine.
Actually, this computable function is not that clear. I mean, what are some functions and which are not computable? Like say I view the computable function like there exists. Say I give the x as the input, and the Turing machine should be able to compute f of x.
Hmm.
And this f is computable. So are there functions which are not computable?
Hmm. Okay. So okay. Hmm. Hmm. So I don't know. This is a vague idea, but for example, so when you say that f should be computable, what you want is there is a total Turing machine that given x gives you f of x. Okay, but what if the function involves, for example, checking whether uh, I mean some machine m halts on that input or something. Um,
Actually, this total Turing machine term is not. I mean, I don't know what this term is, and how this total Turing machine differs from the standard Turing machine.
Oh, okay. So a total Turing machine is basically the machines for decidable languages. That is, for every input, it should either accept or reject. It cannot loop.
Oh, decider. I mean, you mean
Huh.
decider.
Yeah, yeah. So
Okay.
okay. So mm, there is a total Turing machine or decider for f. Hmm. Or other way could be that maybe there could be some counting argument to show that that the total number of Turing machines that you have is only countably many, um, whereas the total number of functions that you can have uh, could be uncount. Okay,
That is for languages, I guess. That the languages are uncountably infinite, and the Turing machines are countably infinite.
huh. But that same argument will work for us because for every function, if let's say f1 and f2 are two different functions, Okay, then there the machines corresponding to them, let's say m1 and m1 m2. Okay, so if f1 is not equal to f2, this implies that m1 is not equal to m2, right? So basically this is a bijection. So if you have n many functions, all the machines, all this set of machines is going to be distinct, because if the machines are the same, then the functions are the same.
Yes.
So if there are too many functions here, but there are only countably many machines that we can have, because these are basically strings over 0 1. So encodings, right? So if we could show that this set is much larger and this set is just count is a countable set, this is something we know, then that would mean that there is a function which is not computable.
Yes. Yes. Right.
But yeah,
Ma'am, total tuning machine means it is countable. So how can we count the total tuning machine as a result?
no, the total Turing machine is a machine for the function f1. Okay, these are functions from sigma star to sigma star, whereas machines are on the right side. So are you talking about these machines on the right side or on the?
Give an example. The sigma star arrow sigma star
I cannot hear you. Could you repeat? Uh,
Yes. Yes. Audible
yeah.
now.
So
Yeah.
yeah, I think I lost my connection, so I'll have to reshare the screen again. Hmm. Sorry, I think the screen is not visible yet.
Yes, ma'am, visible. But ma'am, my question was is that sigma star arrow sigma star. So can you give me an example for this particular machine M1, M2? What kind of representations here involved?
Okay, just give me a moment. So can you see the screen, because I cannot see the screen from my end?
Not
Can
visible.
do you see the notepad?
No. Not visible.
No, no, no. Now not visible.
Okay, maybe I'll just exit and join again. Okay. Is this fine? Do you see the screen now?
Yes.
Okay. Yeah. So you want an example of a function from sigma star to sigma star. So one simple example could be that what f of x does is, let's say, and let's say sigma is 0 1 for us, let's assume it's binary. Then what f of x would do is, it would, let's say, add a 1 before x and output this. So if x is 0 0 for example, then f of x would be 1 0 0, and if x is 1 0 1 for example, f of x would be 1 1 0 1. It just, so this function for example, what it does is it just adds a 1 before whatever the input is. So you can imagine any, I mean any kind of function, basically given some strings here, it's going to tell you what to map it to on the right hand side. That's it. This is your f.
The function of x equal to 100 means uh, what is I could not clear here.
Okay, so a function is always, so you'll always see two sets, one on the left side, one on the right side. So this set on the left side is your domain. Okay, so these are the inputs that the function is going to take. So here for example, the domain for us is sigma star, so these could be any input strings. Okay, and what the function does is it tells you what to map it to. So for example, if the input to you is 0, okay, all these strings are here, right? That I mean, you agree that, right? So there are so many strings here. What it tells you is, okay, if you look at 0 here, what you do is you map it to 1 0. If you see a 1 here, what you do is you add a 1 before it and map it here. Similarly, if you see a 0 0, you add a 1 before it, and so on. So every element on the left side should get mapped to something on the right side. That's what it says.
Okay, ma'am.
Okay.
This is mathematical, like mapping function like that.
Yeah, exactly. It's the same function. Yeah, yeah, yeah. The same definition. And yeah. Yeah. Also, Goyal, to answer your question, I think this argument would work. On this side, we have these are machines which are basically subset of 0 1 star because they are encodings. So this set is countable. Okay, whereas if you look at the set of all possible functions, then for every element here you have sigma star many choices. Okay, um, and uh, this will happen for each element. So this will happen sigma star many times. So this is nothing but sigma star to the sigma star, which is uncountable.
Yes.
So
Right. So,
yeah,
yeah, will it be 2 raised to the power? No.
no.
Sigma is 2 raised to the power sigma star. Right. Yes. Thanks.
So yeah, so therefore there exist there exist functions that are not computable by total Turing, by deciders. Okay.
So in this reduction, the notation we use is this less than and then m. M symbol is being used in the subscript. Could you note that this
Here,
reduction is many to one kind of
yeah,
the
yeah,
reduction?
yeah. I don't know if it's above or below, but yeah, this M denotes, if you see this, that means F is many one. I'll write it in a different color. So if you see M, that means F is a many one function.
And many one would mean that single instance of A can be mapped to no many
No,
instance
many
of
instances of A can be mapped to a single. Yeah. In other words, F is not a bijection.
O. So if F is not a bijection, then can this ever happen that B can also be reduced to A? Like A is getting reduced into the B, and in which situation we would be able to reduce B into A as well, because the function is many to one. So the inverse, would be easy to find unless
Hmm.
the both A's and B's are the decidable ones.
Hmm. Yeah. So
Okay.
in fact, if f is many-one, then f inverse is not defined as it's not a function at all.
Will not be a function except when A and B both are decidable ones. If A and B
Mm,
both are decidable ones, then even with the many to one mapping, since the complexity is same, both are decidable. So in that case, probably if A can be reduced into B, then B can also be reduced into
yeah,
A.
but that could be via some other function g. It's not via f inverse.
By some other function,
Yeah,
right?
because f inverse is by definition not a function. I mean, even if we don't look at a and b, if f is many-one, then f inverse cannot be a function at all.
Yes. Right.
Okay.
Ma'am, how clearly would it need to be explained for us to gain a understanding of the diagonalization argument?
Um, I don't understand your question. Sorry, you.
Actually, what is diagonalization argument means basically? We have
Okay.
written one, two.
Okay. So basically, diagonalization argument is a method which has multiple uses. One use case is to show that that a language is undecidable. Another use case, which is where it originated, was this where this thing we saw last time. Um, so let's look at this thing. Okay, so this is our function f from s to t. Okay, s is the domain here and t is the set on the right hand side, and f tells us how these elements are mapped. So given an element of s, where will you map it to in t? Okay, and and we define what is bijection. So a function is a bijection if every element here has um, has a unique element on the right hand side. Okay, it cannot be that two elements get mapped to the same thing. That is this first condition. This that is this condition. Second condition is there cannot be something here which is left out, which does not have a blue edge going out. Okay, everything should be covered, then you say that it's a bijection. So what we did was we started with the set sigma star. So assume sigma is 0 1. We want to show that it is countable. So when do you say it is countable? If there is a bijection from the set of sigma star, which is 0 1 star, from this set on the left to some subset of the natural numbers. Okay, and then we came up with a bijection of we came up with a function for showing this. So what was that function? The function was simply prepend a 1 before your numbers, and that's how you are going to map it to the natural numbers, to a subset of natural numbers, and that's how we show that it's countable. But if you want to show that something is not countable, that means there cannot exist any function like this. There cannot exist any bijection. Then how will you do that? Because there are so many functions we just counted, right? There are uh, uncountable many functions. So for each of them we cannot show that, oh, this does not work, this does not work, therefore a set is uncountable. So therefore one trick that we know for showing that a set is uncountable is that is a diagonalization argument by Cantor. Um, so what you do is you look at the power set of sigma star. That means you look at all the subsets of sigma star. So these are infinitely many subsets of sigma star. You want to show that this set is uncountable. Okay, so what you do is you write your subsets here. Okay, so all these subsets, so for example this empty set is here, let's say this set is here, and so on. Okay, you uh, you write down all the sets on the in the rows, and the columns are all the elements that you can have. Okay, these are all strings over 0 1. Okay, is this much clear? uh,
Yes, ma'am.
Huh. Okay, then what we are going to do is we are going to fill this matrix. These are the rows, the sets are the rows, the elements are the columns, and we are going to fill the elements with 0, 1 values. So when do you write a 0? You look at an entry, let's say s1, comma 1. Okay, you ask if this element is in the set s1. If it is there, then you write a 1. If it's not there, then you write a 0. So you keep on doing this for every row and every column, and that's how you're going to fill the entire matrix with 0, 1 values. Okay, now here comes the argument, which is that you look at the diagonal of this matrix. Okay, it's an infinite diagonal because this is there are infinitely many rows, there are infinitely many columns, so you're just going to keep looking at the diagonal entries. Okay, and let's say that this entry is 0. What that means is 0 is not in set S1, therefore we wrote a 0 here. So what you do is you create a new set S where you're going to put a 0 because it was not in S1. Okay, then you look at the second entry of the diagonal, which is this 0. Again, what it means is 1 is not in set S2. So since it's not there, we will put it into the new set. Okay, similarly we look at this thing, again 0, 0 is not in S3, so we are going to put 0, 0 here. But let's say 0, 1 is in S4. Okay, since it's in S4, we are not going to put it into a set. So it's basically flipping the membership of the diagonal entries. If an element was there, you're not going to put it. If it was not there, then you're going to put it into your set. Okay, now the argument is that this set cannot be in this infinite list, because at every point, with every set, there is some place where it does not agree with that set, right? Because let's say I look at S4, then I look at its diagonal entry, and this element was there in S4 but it's not in S1. That's how we created S. With every set, there is going to be some mismatch. Some element is either in that set but not in S, or it's not in that set but it is in S. So S cannot be in any of these um, in this entire list. Okay, but we claimed, our initial claim was that, oh, this set, this power set, which is the set of all subsets, is countable, therefore there should be some way of listing them, some way of having a bijection with the natural numbers, which which is a contradiction to the fact that, oh, there is some set which was not in your list, therefore the set cannot be countable. And then, I mean, it got its name from the fact that you are looking at a diagonal, but it's not necessary at all to look at the diagonal. I mean, the same argument would work if you look at some other entries. I mean, you can take this, then you can I mean, you can say, I'll take the first element, I'll take the third element, then the fifth element, seventh, and so on. It's not necessary that you just look at I comma I entries, but it's just easier to argue this way.
Which purpose diagonalization will I use?
Huh. So one thing is to, one application is basically what we showed just now, to show that, for example, this set power set of sigma star is not countable. Okay, and this comes heavily applicable in a lot of areas in combinatorics. So like, you want to know whether a set is countable or not, it has direct connections to a lot of things. So I mean, it's something that's extensively, yeah, you can compare two infinities. You so yeah, if you have two infinities, you want to know which is larger, then there is a yeah, it gives you a way to say that, okay, this infinity is possibly large. I mean, basically what we did here, right? This was an infinite set and this is also an infinite set, and this tells us that this set is larger. Okay, other thing is, you apply the same argument to show that this halting problem is not decidable. Okay, I think did we go over that last time? No. Okay, So yeah, you can show that halting problem is not decidable. What you do is you write your set of machines here. Okay. uh, so these machines are nothing but encodings, right? You can encode a machine as a string. So on this side you're going to write all possible machines. On this side you are going to write all possible inputs. Okay, and then you do the same thing. So on this side you are going to write enumerate all machines. On this side you are going to write all possible inputs. Okay, both are countable. And this entry is going to be 1 if m2 halts on x2 and 0 otherwise. Okay, so similarly you will get a 1010 matrix everywhere. Then what you do is you do the same. It's exactly the same idea, which is you come up with a new machine m, which is as follows: m on input x xi, it's going to accept, or sorry, it's going to halt on xi if mi does not halt on xi, and it does not halt on, or let's say, let's just write 10. If mi xi is equal to, let me just call this matrix A. It's not an A, but yeah, m on xi is as follows. Okay, by 1 we mean it's going to halt if that particular, so we are looking at input xi, you look at its the behavior of the corresponding machine and look at this entry. Okay, if it was 0, that means that machine does not halt on xi, so you want your machine to halt. If that machine did halt on xi, then you don't want your machine to halt. So you are just doing the same business here, just flipping the entire diagonal. Okay, and now we are going to say the same thing, that this machine m is not in this list, because with every machine it has something where there is a mismatch in behavior. So m cannot be in this set, therefore um, therefore the problem of checking whether uh, um, I mean checking whether this whether mi on xi halts or not, this cannot be decidable. If it were decidable, then that would mean that this set is uncountable.
So that argument is not that clear regarding the existence of the machine mx, that why this mx cannot exist.
Sorry, what?
Why
Why
this
this
machine
mx?
M cannot exist.
Huh. Okay. So one thing you agree is that these set of machines are nothing but encodings, right? Encodings in 0 1.
Yes, yes.
So that means the set of all machines should be a countable set.
Right.
Okay. So we know for a fact that the set of all machines is countable. Okay, and what we're doing is we are assuming, our assumption is that there is an entry filling machine. What it does is it looks at the row mi, it looks at column xi, and it fills the value of entry of the matrix, which is mith row and xith column, as 1 if mi holds on xi and 0 otherwise. Okay, so what did we do? We assumed that there is a machine which is going to tell us, okay, what are these values. Okay, so we are assuming that, okay, um, I mean there is a Turing machine which given mi xi tells us whether it halts on xi or not, which is basically what the halting problem asks us,
So the
right?
existence of capital A is our assumption that such a machine capital A exists.
Exactly, yeah. So this, the existence of this entry filling machine is our assumption.
Right.
Yeah, and if that assumption were true, then by diagonalization argument, what we have shown is that uh, the set of all machines, by diagonalization argument, the set of all Turing machines is not countable, because we have shown an m which is not in this set. It differs from all the machines that were previously listed. Okay, so that means the set is not countable because it has missed out some elements. So but this is a contradiction to the fact that we know that the set of all machines is countable. Therefore such an entry filling machine cannot exist. That means,
Actually, reaching this contradiction is not there. I mean, from where did we reach to this contradiction?
yeah, it is exactly the same as, where did we reach the contradiction that the power set of sigma star is not countable. So where is the contradiction exactly happening?
So, like, we took all the elements towards the diagonal side, and we got something, and we got something. Why? Because so what this first zero is indicating here, that S1 does not contain zero, is it?
Yes.
And yeah, so we took S2. So then we got a set of the values and which are not, but why did we, which are not the part of any of the subset listed here.
Huh. Yeah.
So that would mean that we have not listed all the subsets and there exist one more, few more, few more. So therefore, this thing is not countable. So how do we use this argument in proving this
Yeah.
undecidability property?
Yeah. So we want to come to a contradiction that the set of all Turing machines is not countable. So we assume that it is countable, therefore we can list all of them exhaustively, one by one. So this is right. This is okay. This is what we assume, that they are countable. Therefore, we can one by one list all of them exhaustively, such that none of them is left. But now we will construct a new machine M, which differs from the behavior of M1 in the sense that if M1 halts on X1, then this machine is going to do the opposite. It differs from M2 in the sense that if M2 halted on X2, it's going to do the opposite. Similarly, it behaves differently from all the machines that were there. Okay, so that means you have a machine which is, you have a valid Turing machine, but it is not in your list, whereas your claim was that all of them are here. So the assumption that the set of all Turing machines is countable is violated, is contradicted.
How?
I mean,
How?
because you assumed that the set of all machines is countable.
That's true. Like say if I collect all the values towards the diagonal side, then what is being indicated by this collection of the values? Like M1 halt, say M1 does not halt for X1, then this entry would be a 0. Say M2 halts for X2, then this entry would be a 1. Right? So in
So what
that
do you
sense,
mean
if
this entry would be a one? Uh,
like you wrote said
so
that's
this
a
is not.
A.
So this has nothing to do with the entry, right?
So then you wrote that a mi comma xi is equal to 0. I mean, what are the possible values? Like, say, what will be the value corresponding to, I mean, at the intersection of m1 and x1?
Yeah, only 0 and 1. So this entire matrix is a 0 1 matrix,
Right, right.
right?
And the 0 here indicates that m1 does not halt for x1, and
Yeah, yeah.
m2, and for m2 and x2, say m2 halts for x2, then its value is 1. And which you are telling that, okay, this is the filling Turing machine, and there is some filling Turing machine and which assigns these values. So how are we using the diagonalization here? That is not clear, because if I collect all the values towards the diagonal side, then what would happen?
Yeah, then you are basically flipping the behavior of this machine. Okay, let me write down all the steps. Okay, so so that we know, I mean, which step is the, yeah. So we want, so okay, so we started with our assumption that the set of all machines is countable. Okay, so then here is a listing, m1 m2 m3 and so on, and we have this, we have all the entries with us. In particular, let's look at the diagonal entries. Okay, so now what we are saying is, I'm going to design a Turing machine M, which is as follows. What does it do? M on input X. So uh, these are countable, right? So I can have some numbering to it. So this is my first input, second input, and so on. I can number them. So M on input Xi. Okay, what it does is, if run, you don't even need to run. So okay, like if mi halts on xi, which basically means that the entry of mi comma xi is 1, correct? Then we are going to uh, then we are going to loop, otherwise we are going to halt. By halt we mean, let's say we are going to accept, halt and accept. This is the new machine that I'm coming up with. So just to show the resemblance, what we did earlier was we came up with a new set S. How did we come up with it? We looked at this entry. This says that, okay, 0 is not in S1, so let me put it here. 0 was, sorry, 1 is not in S2, so let me put it here, and so on. Similarly, um, the what do you say, yeah, um, where was it, yeah, similarly what we are doing is, instead of coming up, I mean, we are coming up with a machine whose behavior is as follows. Okay, we look at the diagonal entry and look at what that particular machine did on x1. What was its behavior? If this entry is 1, that means m1 halts on x1. So what I'll do is, my machine, if mi halts on xi, it's going to loop. And if that machine did not if this particular machine did not halt on xi, then we are going to halt. Okay, so this is just the construction, that, I mean, so far we are just talking about the construction. So is this much is fine, right? uh,
Yes, yes, yes.
okay, now the point
Actually,
is ki,
ma'am, the diagonalization algorithm is a technique used to construct an object that differ from every element in a list, proving that some problems or set cannot be fully captured.
hmm,
Example like undecidable problem.
hmm,
Also, the like that is.
yeah, yeah, that would be one application. So where is the contradiction happening? We are going to say that, see, m is a Turing machine, which is, therefore it should be somewhere here, right? Because we said that the set of all machines is countable, therefore the m must be somewhere here. That's our, by our assumption, m should be somewhere here. Agreed?
Yes.
Yeah. But can m be m1? I mean, could it be that this machine that we have designed is same as m1? It cannot be, because what we did is we looked at what was behavior of m1 on x1, and we flipped the behavior of our machine. If it halted, then we don't halt. If yeah, and vice versa. Then we ask whether m can be in the second row. Can it be m2? It can't be, because it differs in this, in the behavior of on x2. Similarly, on every, in every row we will find some input on which the behavior of m does not match with the behavior of that particular mi which we are looking at. So that means m is not in the set of all, this set of all Turing machines. But that cannot be, right? It's a set of all Turing machine. M is a Turing machine, so M must be there.
Yes. So how does this lead to the undecidability of the problem then?
Hmm. Okay. So yeah, these are two nested proofs. Yeah. So by this entire, by this page, what we are claiming is that, um, yeah, by this page, what we have arrived at is, so the series of assumptions is as follows. We know for a fact that set of all Turing machines is countable. Okay. Then why did this argument work out? Why was it possible for us to conclude a wrong statement? Because we assumed that, oh, I have a way of accessing these answers. Okay, I have a way of telling whether m1 accepts on, halts on x1, whether m2 halts on x2, and so on. We assume that, okay, there is a decider, there is a machine which I can run. It may take very long time, but it will tell us the answer. Only because of that we could do this thing, right? Here we are assuming, check whether mi halts on xi, and then you decide what to do. Okay. But what if I cannot find out the answer of this? What if it just keeps running? M runs on xi, okay, and it it, let's say, does not halt. Okay. mm, what am I saying? Wait, sorry. uh,
Actually, we could understand till that point that there exists one more Turing machine, and so that the Turing machine is not countable.
hmm.
Turing machine is not countable. But we never said that the Turing machine is countable. Why would I make this assumption when I know this thing in advance that the encodings is cleaning closure of sigma? Cleaning closure of sigma is the infinite set. So clearly there would be the infinite Turing machines.
Yeah,
So why would
the assumption was never that. So this is not an assumption. That's what I wrote. So the fact, and we know for a fact that the set of all machines is countable.
the set of all machines? How can the set of all machines be countable? Because if I uh, so how do I represent a Turing machine? So when I represent a Turing machine, the possible encodings would be what? The subset of the Kleene closure of sigma.
Exactly.
And the subset of the Kleene closure of sigma, the possible subset would be 2 raised to the power Kleene closure of sigma.
No. So when you look at a machine, how do you write? So when you wrote all these inputs, this machines are encodings. So how do you represent when we say this? What we mean is this is a 0 1 star encoding of your Turing machine.
Yes. And then, but then this Kleene closure itself is infinite.
No. Sigma star is countable, right? It is infinite, but it is countable. It is countably infinite.
Oh yes. So fact is, you mean to say that the set of the machines is countably infinite.
Hmm. Yeah.
Oh. Yes,
Yeah.
yes, yes, right. So then from this discussion, we found that this is not countably infinite. We can find one more machine.
Hmm.
But then which characteristic is being followed by that machine? Okay, that machine is not one of the existing machine. This is altogether a new machine because we modified the acceptance of the machine in such a way that when a Turing machine accepts, then it enters into the loop, and when that does not accept, okay, then it halts. Right. So then, from the existence of a new machine to showing the undecidability, I mean that part is not that clear because you said that the reason for the existence of the this new machine is was the table filling was a table filling machine.
Correct, correct.
And
So,
because we got, yeah, from here onwards the argument is not that clear actually.
okay, okay. So, I mean, this whole box uh, is the entire argument for us. We started with, we know for a fact that the set of all machines is countably infinite. Then we assume that there is an entry filling machine, because of which we can nicely write these 1 0 values. Correct.
Yes.
Okay. And assuming that this is correct, that there is such a nice machine which will tell us whether the value is 1 or not, which means it tells us whether mi halts on xi or not. Okay. If that were true, then what we did was we came up with a new machine which whose behavior differs from each of the machines in a peculiar way, and we found out a new machine which is not in the list. Therefore, we arrived at a contradiction that to the fact that set of all machines is countable. So, step 1 is something which is correct. Okay, which, I mean, which is a fact. So there is nothing wrong in that step. Then this step is also something that we know. I mean, if the series of statements earlier were correct, then this step is also something that we know is correct, that you apply the diagonalization argument and you come up with a machine which was not listed. So where did the problem actually occur? It occurred in the fact that we assumed that such an entry filling machine exists. So this assumption was incorrect. If the machine exists, then we can nicely write all these 1 0 values, come up with a new machine, and so on. But the point is that such a machine cannot exist. You cannot, given an m and an x, you cannot, um, yeah, you cannot uh, tell whether m accepts x or not.
Actually, this
Oh,
seems to
sorry,
be a
halts
very,
on.
yeah, actually, this seems to be a very clever argument wherein we intentionally made this modification that when the Turing machine accepts that X, then the modified one enters into the loop,
Hmm, hmm,
right?
hmm,
But then, even with this argument, yeah, because I can understand that, yes, I can understand that, yeah, there is other proof also of proving that the halting problem is undecidable, wherein the Turing machine itself is given as an input, and then we reach to the contradiction.
yeah, then, yeah, yeah, the
Actually,
self-reference.
yes, yes. Actually, that is easy to understand. That proof is easy to understand.
Hmm,
But in this proof, because we got one more machine, will negate the existence of the entry filling machine. This last part is not that getting clear. That because we got one more machine, how does it imply that there cannot exist the entry filling machine? It could also be that the first fact is incorrect.
yeah, that cannot happen because this is a true statement, right? I mean, this is a,
Yes.
yeah, so this cannot be wrong because we know this is the, I mean, this is tautology for us.
Okay, now I understood.
Huh.
Yeah. So the only thing, only possibility wherein things may become wrong is the entry information. Yeah, makes sense. Thanks,
Exactly.
thanks. Thank you so much.
Sure. Okay, so I'll just write whatever we discussed. So therefore, by this argument, I'll copy this thing. Hmm. Okay, so this is a contradiction but step 1 or fact 1 cannot be false, so therefore it has to be the assumption. Therefore, there cannot exist a decider which, given input m comma x, tells whether m holds on x. In other words, HP is undecidable. Yeah, so this is yet another proof of the fact that HP is undecidable, right? There is a smaller argument for it, which is, use the self reference, feed that same machine to itself and see what happens.
Yes, yes.
Yeah, actually you can do the same thing in this table itself. You can say that, yeah, I mean, um yeah, you look at the machine m and look at what it does um, on its own input, right? This is also a string, so the same string must appear somewhere here also. You look at that entry and see that, so initially m halted on, so initially let's say the entry was 1. So these are just strings m. When we write m, these are just strings over 0 1, so we can write it like this. So if initially this was 1, that means m halts on this encoding m. Okay, but um, yeah, by flipping the behavior, okay, sorry, I'm okay, maybe I don't recall it right now, but there is a way of seeing that same argument, by looking at the same, I mean, looking at the machine and feeding it its own input, and hmm,
Yes.
hmm,
It can be, but then this requires little more effort, yeah,
hmm,
be done.
hmm. Yeah, but I think, yeah, this argument is there in Sipser also. The one that I explained, the Cantor's diagonalization one, and also the one that you are talking about. Yeah, towards the end of the diagonalization, I think they do remark on this, and you'll be able to see that the same argument within this proof also.
Yes, yes.
Okay, so I'll just erase this so that there's no confusion later. Okay, okay. So yeah, but why did we come here?
So we came here because you told that there are two strategies to prove that the problem is undecidable.
Hmm.
The first one is diagonalization. The second one was the reduction.
Right. Yeah. Correct. So one way to show that would be you go through a diagonalization argument, which is generally a little tricky to come up with, or yeah. Um, so a better way of doing would be, or an easier way of doing it is generally through reductions. And the third way is, of course, the Rice's theorem. Third method would be Rice's theorem, which we will talk about again. Um, yeah. Um, yeah, Rice's theorem would be even easier because it's just a one-step, two-step application to show that a language is not decidable. Okay. Yeah, but the power of reductions is that it can be used to show that a language is decidable. It can be used to show that a language is not decidable. Whereas Rice's theorem, you can only use, even the diagonalization argument, you can only use to show that a language is not decidable. Okay, so yeah. Hmm. Yeah, and there was right, there was this one question that we were trying to solve, and I think we uh, could not finish it or something, right? Sorry, let me just find it. Hmm. Okay, yeah, here. Yeah. Okay, so we had this question, equals is the following language. You are given as input an encoding of a machine M, which is nothing but a binary string. Okay,
Ma'am,
and
encoding on machine A means what represented in this question?
encoding of a machine is basically your machine. By, I mean, the way we defined it, it was a tuple, right? It had states and everything, that 7 tuple definition. But what I'll do is I will come up with a function which will represent, which will encode it. Okay, if I want to write, so your states could be q1, q2 up to q10, right? So what I'll do is I'll encode my states, and let's say that um, um, let's say 1 is my separator. Okay, then this is my first state, this 0 0 is my second state. I'm mapping q1 to 0, I'm mapping q2 to the string 0 0. Then 1 is my separator, and I'm mapping q3 to 3 zeros, and so on. So instead of telling uh, the states like this, I can equivalently write it as a binary string. So I'm encoding the same information in binary. You can use any function you want. This is just one way of representing. Okay, so similarly the entire Turing machine can be encoded into a binary string, and this is what the this angular brackets and M denotes, that it is a binary representation of the machine M.
Okay, fine.
Okay, so yeah, so you are given encoding of a machine M such that the machine M is a DFA, and it accepts some string which has equal number of zeros and ones. So this is something we were looking at. So for example, if you look at this language, this particular string does not have equal number of zeros or ones. This does not have, whereas there is one string which is 0101 where there are equal number of zeros, there are equal number of ones. So this machine, or this machine should be in this language, because there must be some string which has equal number of zeros or ones. Others may or may not have, that does not matter, but there should be at least one string which satisfies the property. Whereas if you look at this machine, the language of this machine, it contains strings of the form n ones followed by n plus 1 zeros. So clearly, by definition, there cannot be a string with equal number of zeros and ones. So therefore, this will not fall into this language. Okay, so this is just one example. This is a non-example. And what we want to do is we want to show that checking that given an M, which is promised to be a DFA, checking whether it accepts at least one string which has equal number of zeros or ones is decidable. This is what we wanted to show. Okay, and um, the way we did that was through reductions. Okay, so like we remarked earlier, if you want to show that a language is decidable, you're going to reduce. If you want to show that language A is decidable, you reduce it to a language B where you know that B is known to be decidable. So that would mean that A is also decidable. So in this case, A for us is this language equals. Okay, so I'll write equals here. So what we need to do is we want to find a good candidate B such that equals reduces to B and we know that B is decidable. So one candidate is something that was done in the lectures. So we will not prove this because this was done. Okay, so we know for a fact that the following language where you are given a machine M which is a PDA and the language of that machine is empty. So checking whether given a machine M which describes a PDA and checking whether its language is empty or not is decidable. This is something we know. So what we were trying to do was we reduce the R equals problem, which is this problem. We want to reduce it to this problem because this is something we know is decidable. Therefore that would mean that equals is also decidable. So our job now is only to show the reduction. Everything else follows. Okay, and I think we just made a small mistake in trying to do that, which was that yeah. So yeah, so you have equals, which is the set of all M such that M is a DFA and there exists X in sigma star such that um, M accepts X and number of zeros in X is same as number of ones in X. This means equal number of zeros and ones. Okay, and what you do is you have this you know that the following language L, which is the set of all X such that um, X contains equal number of zeros and ones. Okay, so what do we know about L? Is L context free?
Yes, yes, it's content.
Right. So L is a L is in CF is a context free language. Okay. So now what will happen if I take, so input to me is this machine M, right? So this is what I was given. This is my input. And let's say L of M is the language of that DFA. So what happens if we take intersection of this language with L, which is as follows? Okay, what do we get?
So, like, say if the language recognized by M is say 0 star 1 star,
Hmm.
and if I take its intersection with the equal number of the zeros and ones, that value would be 0 raised to the power n, 1 raised to the power n,
Correct. Yeah.
and which is CFM.
Yeah. Yeah. In other words, it filters out it filters out those strings from the language of M which contain equal number of zeros and ones.
Yes, yes, right, right.
So this is the set of all x such that x is in L of m, that is, or let's say that DFA m accepts x and x contains equal number of zeros and ones. So this first part comes from the fact that x is in the language of m, therefore the DFM accepts x. And the second part comes from the fact that L is this language which consists of all strings of equal number of zeros and ones. Okay, so okay, just give me a, okay, sure. Okay, so isn't I mean, this condition is exactly what we had over here, right? So m is a DFA such that there is a string which m accepts and it contains equal number of zeros and ones.
Yes.
And so what do we know about this language? We know that L is a CFL. We know that this L of m is a regular language because m is a DFA. What do we know about the intersection of a regular language and a CFL?
That would always be safe.
Correct. So we know that intersection of a regular language and CFL is a CFL. Okay, so therefore on this side we have a language which is a CFL, and you want to check. So this is our um, yeah, basically what I mean to say is how are we given this regular language? We are given it in the form of m. We are given a machine, and can I come up with a machine for L? We can always come up with a PDA which checks whether the number of zeros in a string are equal or not.
Yes.
So I have two machines, one is a DFA, the other is a PDA, and by cross product construction you can come up with a PDA for the intersection language.
Right.
So use the cross product construction to obtain a PDA for L of m intersection L. Okay, now all we want to check is whether this language is empty or not, because if it is empty, and okay, let me just call this new machine as m prime. Okay, so L of m prime is nothing but this language that we wanted, intersection of the two. Okay, let me call this L0 so that there is no confusion. Okay, so I have this PDA m prime. Okay, now if L of m prime is empty, what does it mean? It means that there does not exist a string x in sigma star such that m is the DFA which accepts x and the number of zeros and ones are equal. If this is not empty, okay, then what that means is there is indeed a string. I'll just write such a string exists. Is this fine?
Yes.
Okay, then all we want to do is, given m prime, we are just asking for emptiness checking. Given a PDA m prime, so this problem reduces to the following: given a PDA m prime, check if L of m prime is empty or not. If it is empty, then we know that the answer to this is yes. If it is not empty, then we know that the answer to this is no. So that is basically the spirit of reduction. We are solving some other problem to get our solution. And this problem is exactly what is this EPDA, which is what we defined here. mm, yeah, this is exactly what we defined. EPDA is the following problem: given a PDA, check if its language is empty or not. And this is something we know is decidable. So
Yes.
this is
Actually, we
important.
know that. Yeah, actually, we know that ECFG is decidable, but then for every CFG, since we can construct the PDA, so therefore EPD is also decidable, right?
This is decidable, therefore our original problem equals is decidable. So just to summarize, what we did is, we have this language equals, we want to show that it is decidable. So what we do is, we are going to reduce it to the emptiness checking problem for PDA. How do we do that? um, yeah, so we observe that this um, so given a machine M, okay, which is a DFA, if you take its intersection with the language which consists of all inputs of equal number of zeros and equal number of ones, then that set is nothing but it's same as checking whether there is a string with these properties that we wanted. And we can come up with a machine for this, which is a PDA. This is something we know how to do by cross product construction. So all we need to check is whether the language of this PDA, which recognizes this intersection language, is empty or not. If it is empty, then we know that such a string does not exist. If it is not empty, then we know that such a string is there. So this is nothing but, so since we are only checking for emptiness of a PDA, this is nothing but the emptiness checking problem. So for solving equals, we are reducing it to emptiness checking problem, which we know is decidable, therefore equals must be decidable. I think um, the mistake we did last time was that we did not take the correct language to take intersection with. Instead of taking this, I think we took 0 to the n, 1 to the n, which just does not work for us. So
Yes.
yeah, so this step was not correct. Yeah,
Yes.
so maybe I'll just delete this so that there's no um,
Yes.
okay, so now, yeah, this is complete. Okay, yeah. And yeah, this should be similar. um, yeah, this is again similar. What you'll do is, L of m is the language of this machine M. You need to find L0 now. So this is the only thing that's going to change. So what should be L0, so that L0 intersection Lm, okay, this corresponds to just checking whether, so what you want is, when this intersection is empty, there does not exist a palindrome which the DFA accepts, and when the intersection is non-empty, there is a palindrome which the DFA accepts. So what should this be?
So which language should I select so that its intersection with the palindrome will came out to be will came out to be a CFL? So I need to select a regular language and whose intersection with the palindrome came out to be
So
again.
you're not selecting the regular language because it is given to you. So this part is fixed for you because input is m. So L of m is fixed, m is fixed. You just need to choose L0 such that the intersection of L0 with this language
Yes.
captures this.
So L0 would be WWR. WWR is the
Exactly.
palindrome.
So this is L0 is nothing but the language palindromes, which is set of all x such that x is a palindrome. So when you take its intersection, this language is nothing but the set of all x such that m accepts x and x is a palindrome, which is exactly what we wanted here. These two are same. So now all you want to do is, if L0 intersection Lm is empty, then yeah, then your answer is no. If this is not empty, then your answer is yes, similar to what we did earlier. So that means you have reduced the instance of, what was this language? Okay. So you have reduced the instance of PALs to the language of EPD, sorry, EPD, right? Yeah. So you're just going to check for the emptiness of this, and this is decidable. Therefore, this is decidable. And all the arguments are the same. The only thing we changed was this language L0. Instead of taking equal number of zeros and ones, we took it as the language palindromes. Every other argument, every other step is exactly the same. Why is this a context free language? Because intersection of regular and context free is context free. You can use the cross product construction to find the machine m prime for which you want to do the emptiness checking. Everything else is the same, just that we identified a different language.
Both the problems are very interesting indeed. Yeah.
Right. So this is a demonstration of using reductions for showing that a language is decidable. Normally the more frequently seen use case is when you want to show that a language is undecidable, then you would reduce to some undecidable problem. But yeah, this is the other way around.
And most of the time, that undecidable problem is either ATM or halting problem. This is
Yeah.
yes, yes, right.
Yeah, because these reductions are transitive, right? So if you can reduce a to b and b to c, then you also have a reduction from a to c. And normally the first problem we start with this halting problem. So yeah.
Yes, yes.
Yeah, and this thing is also exactly the same. I think you can just look at what L0 should be. L0 should be the set of.
Some string with more A's than B's. Yeah, we solved this problem and we proved this language as non-regular using pumping lemma in your session. Yeah.
Right, right, yeah. But this is a different problem that, oh, you mean this language?
Yes,
Sure,
yes,
sure,
yes.
yeah, yeah. Not regular, but it's a CFL.
Yes, yes.
Okay, so coming back to, okay, I need to okay, maybe let's do this other question.
So, would it be possible for you to include in your notes, maybe today's, maybe in the next session, the difference in between the many-to-one reduction, the car reduction, and then Turing reductions? Because three reductions are given are being used in the lectures. So, one is the reduction which is being discussed today, that is many-to-one, and the other one is a car wherein the time matters and the complexity, and then there is the Turing reduction wherein we can query to multiple times, we can make queries, I guess.
yeah, yeah.
So if you can write in your notes, I mean, that those, I mean, distinctions clearly and their possible use. So yeah, maybe in the next session we
So
can
is
put it.
that in the content of week 9 or week 10? Um,
Nine, week
9.
nine, week.
Okay, okay, sure. So week 9 would mean, yeah, Monday
ECT,
7 p.m.
Monday session. Monday is tomorrow only.
Yeah, yeah. So, okay, okay. So, we will define a new machine which is called enumerator. Okay, so what does it do? It's basically like a printer. Okay, there's no input to it. It just keeps printing infinitely. Okay, so this is the machine that we have, and it keeps printing some strings. Okay, it may repeat. Okay, and there is no fixed order in which it's going to print. Okay, so it's not lexicographical order or anything. It prints in any order, and it can repeat strings. So for example, maybe it printed 1010 here, it can print it again after some point, and there's no such concept of halt or something. It may infinitely keep printing, or it may even be the case that it just keeps printing the same string infinitely, so it just maybe prints 0 all the time. Okay, so okay, so we
Ma'am, you were telling 0 all the time, it will printing zeros. Why not 1? When print 1? When it's printed 1, 1, 1, 1, 1, like that.
you can so the definition of the model is just that it's going to print it's going to keep on printing strings like this by separating with hash or something. It can repeat and so on. I'm just saying one example of such an enumerator, one such machine could do that. It could just be printing 0. This could be one such enumerator. Some other enumerator could be doing 101 and so on, or some could just be doing 1. I mean, you can come up with your own definition of what strings you want to print and what in what order you want to print. Yeah, this was just an example.
Okay, ma'am. Okay, understood.
Okay, so yeah, for example, this particular enumerator prints these strings. Okay, and it can keep on printing infinitely. So okay, so that is one model. You have one machine, you know, is this enumerator, which is basically a printer sort of, yeah, which keeps on printing strings. The other machine which you are um, yeah, which you know is the Turing machine, which is the standard model. You have head, you have tape, which is infinite, and you can keep on writing and so on. Okay, so you know what are and of course by I mean, so if you look at the set of strings that are printed by this by an enumerator, it forms a language, right? It's a subset of sigma star. So if a language is um, printed by an enumerator, you say that it is an enumerable language. Okay, and Turing recognizable languages are the ones for which we have Turing machine, which need not be total, which need not be decidable. It's a Turing machine. If X is in the language, it should hold. Okay, so on one hand you have this Turing recognizable languages, on the other hand you have enumerable languages. You want to show that they are equivalent. Every language which an enumerator prints, okay, for every such language there is a Turing recognizable language. You can come up with a Turing machine which um, accepts the same language, and the other way around. For every Turing machine that you give me, I can come up with an enumerator which is going to print all the strings in the language. It may print repeatedly, it may print in any order, there is no fixed ordering, but it will definitely print all the strings and only the strings in the language. Okay, so these are the two parts. So is the statement of the, I mean, is the definition of enumerator, sorry, and the statement that we are making, is that clear?
So definition of enumerator is not clear. I mean, what
Okay,
this enumerator is doing,
it
and
just,
how can
huh.
we define this enumerator, like say mathematically? What is, I mean, what I mean, how does it differ from the Turing machine?
So the model of computation is different, right? This enumerator does not do any computation. There is no input to it. It does not look at, there are no states or anything. There's no computation at all. It just keeps printing strings.
Okay, so even if it keeps printing, its name is enumerator, so some kind of enumeration must have been there, is it? Or what kind of the enumeration is there?
Um, I don't understand what kind of enumeration as in.
So because its name is enumerator, so must be enumerating something, isn't it?
Yeah, it's enumerating some language, some subset of strings.
Oh, I see. Random strings.
Um, so you can, I mean, for any language you want, you can define an enumerator, right? If you want it to, for example, if you want um, this particular language, then I can define my enumerator which will accept this language. So what will that enumerator do? It will check if maybe like go through all possible strings. We know these are countable strings, so maybe it's not necessary that it goes in that order. In that order, it can do whatever it wants. One possibility is it goes through all the strings. It checks if one of the strings matches with um, the language L. If it does, then it will print. Okay. If it doesn't, it
So do we have different enumerators for different languages?
yeah. So enumerator is a model for a language of your choice. You can come up with an enumerator, or for the same language you can come up with two different enumerators. One enumerator could be, let's say, printing in this order. The other enumerator could be printing the same language, but maybe some strings are repeated, order is different. So this is E1, this is E2. They are different because they print in different orders, but the language of E1 and the language of E2, they are the same. That can also happen.
Oh, I see. Now it's clear to me. So in this sense, whatever is being recognized by the Turing machine, in fact, is the whichever language is enumerated by this enumerator. Both are same.
Yeah, yeah,
Because if a string is not the part of the language, that can only be, I mean, then the Turing machine may enter into the loop kind of the thing, and that is the subject matter of the Turing machine as such. Enumerator has nothing to do except displaying all the strings, maybe in the random order, but then those strings would be the part of the language.
yeah,
Yes, all right.
yeah, and
Probably
it
that
should,
is why, yeah.
yeah, it should only print strings in the language and all the strings in the language. It should not print something that's not in the language.
Yes. And that is how this Turing recognizable is also called the recursively enumerable. I don't know
Exactly.
from where this recursively terms appear, but
Yeah, yeah. I'm not sure. Yeah.
yes.
But yeah, you are right. So that is where the enumerable term comes from. Mm,
Yes.
yeah. So one direction should be easy. Uh, Given a Turing machine, you should be able to. Um, yeah, actually, both directions are very similar. So
Both directions are similar. Yes. Yes. Right. Yeah. And what that BG Weaver problem is something related to this enumerator or something else. I don't. I just know the name of the problem. I don't know what this. I mean, what the problem as such is.
which problem?
Probably, but BG Weaver problem or this infinite one. No, wait.
No, can you define the problem?
No, I don't know the problem formulation. But then
Oh,
probably I heard this problem maybe in the context of the enumerator sometime. I don't know. I don't
I see.
remember actually.
Okay, okay. I'll Yeah, I'll look into it.
Yeah, sure.
Okay. So, yeah. So, maybe I'll not write the rest of the things, but let's just go over this thing. So, you are given an enumerable language. So, there is an enumerator for that language. Okay, you are given this enumerator, which what it does is it keeps on printing. You want to come up with a Turing machine for the same language. So every string that is printed should be accepted by the Turing machine, and it should not accept anything that is not printed by the enumerator. So let's say you have an enumerator E, and let's say the language is, yeah, it's the language of the enumerator. Okay, we want to come up with a Turing machine M such that the language of M is same as L. Okay, so what does it do? M on input X. What does it do? It's going to run E. Okay, so you can't run E on X because E does not take any input, it just prints, keeps printing strings. Okay, and what you do is, if the output of E matches with X, then accept. And you are going to keep on doing this, you're going to keep repeating this. Okay, that's it. So what that means is, so you have this enumerator, it's going to print some string. Okay, you check if what your Turing machine does is it checks whether that is same as X. Let's say X that was given to us was 10101. Okay, check if 10101, this is where we are going to check whether the output matches with the input. It does not, then what you do is you repeat, look at what is the next string that it prints. So there is a separator, it prints something else. Okay, again check if this matches with X. If not, then you keep on repeating. There are infinitely many strings. If the enumerator ever prints X, which is let's say 10101, then it will be caught in some step, because you are doing this serially. Okay, then definitely at some point you are going to accept. Okay, and if a particular input X was never printed by E, then what will happen is you will just keep on checking whether the output of enumerator matches with X. It will never match, so you will never end up accepting, because this condition itself will not hold. Okay, so therefore the language of M is the same as the language of the enumerator, because it is accepting only those strings that are uh, enumerated by E, and everything else is not accepted. Okay, so the other direction is also very similar. um, so can you maybe just, if you have any thoughts on how to do B?
Ma'am, this question is not quite clear to me, so could you please explain it thoroughly?
Is the definition of I mean, the definition of Turing machine is fine, right? So is the definition of enumerator also clear?
Yes, yes, ma'am.
Okay.
It keep doing printing, not finitely.
Yeah. So what this question is saying is that, as a model, enumerators and Turing machines are the same, meaning for every Turing machine you can come up with an equivalent enumerator. What we mean by that is, there is an enumerator whose language is same as the language of the Turing machine that you had, and the other way around is also true. For every enumerator there is an equivalent Turing machine. So if you give me an enumerator E, I will be able to give you a Turing machine M such that the languages of both of them are the same.
Ma'am, equivalent tuning missing basically what message let's keep
Yeah, equivalent meaning that when you say two models are equivalent, every language that can be computed by model M1 can also be computed by model M2 and vice versa. Okay, so
can you repeat ma'am please
yeah,
once again?
yeah, sure. So let's say this is the set of all languages that the enumerator. Okay, is there a lag in this? Yeah. Okay, this is the set of all languages that an enumerator can accept, and this is the set of all languages that Turing machines can accept. Okay, so let me call this S1, let me call this S2. If S1 is equal to S2, then and we say that enumerators are equivalent to Turing machines. Basically, the set of languages that enumerators can compute is the same as the set of languages that Turing machines can accept. Okay,
Okay.
so this is this term you might have also come across when we talked about models of computation for regular languages. For example, we talked about DFAs, we talked about NFAs. We say that they are equivalent. DFAs and NFAs are equivalent because every language that can be computed by a DFA has an NFA for the same language, and the other way around is also true. For every NFA there is a DFA which computes the same language. So they are equivalent models. Okay, so now is the question clear, like the part A and part B? So this is basically asking to show that they are equivalent. Everything that an enumerator can compute can be computed by a Turing machine, and everything that a Turing machine can compute can be computed by an enumerator. So uh, yeah, so this proof is for only for part A. For part B it's very similar. You just have to um, take care of ordering, that's all. Ordering in the sense, yeah, I mean you'll figure it out if you when you try to solve it. Okay, but if there is any doubt, then yeah, then you can ask me in the, yeah, in the next session. Okay, so next we'll meet on um, yeah, Monday, which is 23rd March, same 7 p.m. to 9 p.m.
Which topics shall be covered tomorrow? Yeah, PCP or in the week 9 in the lectures?
Yeah, we will stick to the content of the week 9. I've not looked into it yet, but yeah, yeah. I mean, do you yeah, do you want something specific to be covered other than
No, no, no. I mean, the general content is fine. The PCP thing.
sure.
Sure. Thank you
Okay,
so very much. Thanks.
thank you.
Good. Bye.
Good.